All right. I'm just gonna wait a second to see if the streams start. And looks like Twitch is live and there is YouTube. Good afternoon, everybody, or I guess morning, wherever it is in your time zone. I hope you're having a nice day. I'm finally feeling better, and it's great. It's great. I'm happy to be healthy. It's a nice change of pace. And we are going to be doing something a little bit different today. I am going to be talking a little bit more to a sort of earlier in their journey audience. One sec, let me make sure I can see all the chat messages. And we're going to be talking about machine learning in general, sort of high-level stuff. What do you need to do? What should you watch out for? When is it appropriate? When is it helpful? When should you use deep learning? When would maybe a different technique work? And then we'll start going through an example with XGBoost, which is a specific algorithm for which can actually be used for classification or regression, but we're going to be using it for classification today. Prathaban says 4:30 in Chennai. I'm assuming that's PM. If it's 4:30 a.m., then thank you for waking up. That's really early. No, it can't be 4:30 p.m. because it's 4 o'clock here. So it must be a.m. Well, good morning then. You're up early. So to start off, I actually made some slides, and I had made some materials for this is ever so slightly not a good size. There we go. So you can see the whole screen. I'd made some slides for the workshop I wasn't able to give in Indiana because I was too sick to travel this week. So I've got slides today. I don't usually have slides. To start out, so we're going to be using R today. And if you are already using R, you probably have a background in statistics and you're familiar with inference. So statistical inference. And the sort of general idea of statistical inference is that you have a sample which is drawn from a population, and you want to know about the characteristics of the population from which it was drawn, and if that differs from a different population in general. So I would describe the sort of task that you are doing when you're doing statistical inference as quantifying uncertainty, and you're doing this analytically. So it's something that you can write an equation for and then solve. So it's pretty tractable. And this is in contrast to machine learning. And even though we're using the same techniques and the same sort of like underlying math in both of these fields, the sort of like the premise of the field is a little bit different. That's why I'm sort of giving you a high level introduction here. And in machine learning, the task is more along the lines of taking a sample that you're given. So in both cases, you don't have access to all the information about everybody. Usually you have some sort of subset of the information you're interested in. And you want to build a model that can predict a quality that you're interested in other samples. So instead of doing things analytically so that you can solve an equation, generally we do things numerically, so through sort of simulation. And the thing that you're doing is you're not quantifying how uncertain you are about your analysis. You want to predict unseen data. So that's a pretty distinct difference between the two fields and sort of their general approach to what the core problem of the field is. And so if you have an R background, you probably have done some statistical inference. You might have a science background. You might have biostatistics or chemistry or sociology or econometrics or population studies or demography or whatever your background is that caused you to want to learn R. That's probably going to be more inference based and statistically based, and probably a little bit less machine learning based. So we're going to be talking about machine learning today rather than statistical inference. So even though a lot of the, again, the math is the same, we still have, classification and regression and those types of tasks, the approach and sort of the tolerance for what's important is going to be a little bit different. Inta says, brand new MS in analytics student here. Oh, welcome to the field. So in machine learning, we tend to talk about it being either supervised or unsupervised. So it's probably the highest division of types of machine learning approaches. So in supervised learning, you have labels that you're interested in. So this could be either the group label. So you might want to use classification to assign a specific data set to a group. So an example of that might be whether an image is a cat or a dog. So that's sort of a classic example of an intro machine learning question. Ashkit says hi from Boulder. Hello. Or you might want to predict some sort of scalar quality, so using regression. So given the dog's weight, and so you want to predict the dog's weight given the age and the breed of the dog. So you're giving other information to predict this sort of this scalar thing. Is one type of supervised machine learning problem. The other sort of broad class of machine learning problems, more or less, they're sort of like other interesting types of problems that aren't really supervised or unsupervised. But another type of, in unsupervised learning, you don't have information about the label of interest. So an example of unsupervised learning might be clustering. You have a bunch of measurements about a bunch of different data points, and you want to discover if there's any patterns. So an example of this might be you have analytics data for a bunch of incoming students for a class at college, and you want to say, decide what houses to put them in. So you use clustering to be like, oh, these people are alike, these people are alike. Maybe we want to have like a good mix from these different groups based on sort of like where they're from geographically, or interest areas, or whatever it is that you're interested in sort of diversifying. Or you could do dimension reduction is another type of unsupervised learning. And this is where you have very high dimensional data. So maybe you have sensor data and you have 40,000 channels in your sensor, and you want to compress all of those channels down into just sort of three vectors that you can look at over time instead of looking at 40 vectors over time, so you can do things a little bit faster. So that type of dimension reduction, you don't have labels like which ones are more important. You can sort of deduce that information based on what's more informative given the information you have. So that's sort of the broad overview of the types of things that you do in machine learning. One particular class of algorithms in machine learning is called deep learning, and you can use deep learning for supervised. So I'm trying to think of unsupervised tasks that you can do with deep learning. I guess language modeling is technically an unsupervised task usually. So that's when you're determining what words tend to occur in what order in a language. Usually it's supervised learning. And the reason that deep learning is exciting is that it is a way that you can, without having to specify anything, in theory, approximate any function. So if you have a bunch of data points, the relationship between them can be described by some function. There exists a function that can describe them, and you can use a deep neural network, and if it's sufficiently deep and sufficiently wide, whatever function it is that best describes the relationship of your data, in theory, a deep neural network can find it. And a neural network is deep when it has one or more hidden layers. A neural network with only an input layer and output layer is a sort of inefficient way of doing linear regression. And we've done some reading group videos previously on why deep neural networks work and sort of going through the math. Jer says an autoencoder could be an unsupervised learning task. Oh, yeah, that's another good example. Thank you, Jer. practically, there are some limitations to using deep neural networks for everything. So one is that because you have so many little cells and each cell has, a bias and it's got all weights from all of the other cells below it that feed into it, there's a lot of things that you need to train. And there's also a lot of things that you can use when you're specifying the model, hyperparameters, which are some quality of the model. So maybe depth, maybe number of cells, maybe the specific algorithm you're using to say, oh, there's an error. How are you going to correct the error going back through the neural network? And because there's so many different things and we don't really as a field have a good idea of what hyperparameter settings are going to work well for what problem before you start working on the problem, you have to do a lot of guess and testing. And this is part of the reason why Kaggle competitions are so interesting, is because we don't have this principled understanding. So even if it's a problem and we're pretty sure that deep learning is going to work really well for it, you don't necessarily know how to build a model that's going to work well for this particular problem without spending some time exploring the parameter space. And they also require a really large amount of training data, and especially labeled training data. So for because you're not sort of like looking at an image and deciding what the rules are for finding like a box. Like if you're building you're trying to detect packages on a video feed to let somebody know whether or not their package has arrived, for example. So you're looking for boxes. And if I'm telling a human how to do this, I can say like, oh, hey, look for like a shape like this. That's probably a box. Or look for the color brown. So you don't need to give a human a lot of training examples to get that down. Because you can't give that sort of structural information to a neural network, it needs to see enough pixels that are within boxes that it can determine what that's going to look like in a variety of lights, a variety of different backgrounds. So a lot of training data is required for neural networks in particular because of the way the training works. And there's some ways to augment smaller data sets, but they take time and it takes longer to train. The more training data you have, and usually the more training data you have, the better output you will get. And at least in language sort of tasks, we don't seem to have found the upper bound of that, which, considering the size of the text data sets that people are working with these days, like billions and billions and billions and billions of words of text, and you may not have that for your specific problem. So that can be a big bottleneck for people. And in general, the more complex the thing that you're trying to do, the bigger the model is going to need to be, and the longer it's going to take to train, and possibly, depending on how you set it up, the longer it will take to actually give you predictions at the other end. So the more complex your model is, the longer it takes to give you each prediction. And then there's some other qualities as well. So if you have a model that's looking at a sequence and it needs to look at the item that happened before this item to tell you its prediction for this item, that's going to be a bottleneck because it's going to have to step through. So those are some drawbacks of neural networks specifically. I know a lot of people come into the field and are really excited about machine learning, and they've heard a lot about deep learning, and they're like, hey, has had such good results, and these are some things to think about. So when would I recommend using deep learning for your particular work? So my personal litmus test at this point is it should be something that a human can do with minimal training in less than a second. The longer it takes a human to do, the more complex the task probably is, the bigger the model. Ooh, I've added a slide. The bigger the model is going to have to be, the longer it's going to take to train, the more training data you'll need. So things that are easy and fast for humans to do are probably where we're going to see a deep learning model doing fairly well pretty quickly. Also places where I have a relatively high tolerance for unpredictable errors. Deep learning algorithms, the output of deep learning algorithms, the models themselves, don't work in the ways that humans do. So if I ask you to look for an elephant in a picture, you're going to look for the silhouette of an elephant because that's the way that human perception works. But a deep learning model, a deep learning trained vision model, is going to look for pixels that resemble pixels it has seen together in other images where it's seen elephants. So it could actually be looking for an acacia tree in the background if you've only shown it pictures of elephants with acacia trees. Or it could be, it might recognize this sort of like crinkly gray I have on my sweater here as an elephant because it looks like pixels it's represented, it's seen previously when you've presented it with elephants. So you're going to get weird errors, especially in language models. And just know that that's going to happen. And if it's a place where you don't have, like, it's not life or death, that's probably, I'm more likely to use a deep learning model. So some examples. I'm pretty okay with using a deep learning model for copy editing. So things like finding typos, especially if it's a language where I don't have a good spelling engine already. That's pretty straightforward. A human can do that quickly. It's not super complex. For something like detecting whether or not something is plagiarism, you can definitely look and see whether there's been copying, and you don't necessarily need deep learning to do that. But this is still pretty straightforward. It's pretty fast for a human to do. It would be more difficult to build a deep learning model for this, but potentially a place where it's okay, especially if you're not sort of like charging people with a crime if the model does says that they did a plagiarism. And an example of a place where I would not use deep learning is grading essays, because that's something that's very complex. It requires a lot of sort of like common knowledge in the technical terms, so sort of information about the world and the ways things work, and that's very difficult to do in a deep learning model, and that's the sort of thing that would make a really good Kaggle competition, because it is so difficult, because it's going to require so much work. And also an aside, I get a lot of questions about creating deep learning models to do OCRs, that's ocular character recognition, so getting text out of images. There are a lot of commercial products that will do that much more fast and easily than you building that yourself. And your time's not free, and depending on your particular circumstances, I think it's probably going to be easier for most people the vast majority of the time, especially if you're doing this for work, if you can use a commercial product that exists. So another example would be voice recognition. There's some fantastic voice recognition APIs out there. Google's really good. No, I know Microsoft has one. I think one of the Alexa voice APIs is out there. So you have a lot of options for voice APIs, and I wouldn't build a voice recognizer from scratch, even though that's what's in my background, what my background's in, because it's too much work to get it working well, and someone's already done it. So, once you have decided not to learn to use deep learning, I've got a talk upcoming at PyCon on sort of things that you can do instead of deep learning. Thank you. Sumachan says optical character recognition. Yes. I don't know what I said. Oh, I probably said ocular. Yeah, optical character recognition. The sort of machine learning workflow is always going to look more or less the same. So before you begin training your model, you want to split your data into training data and testing data. And the testing data you sort of like put in a little Christmas package and just leave it alone and don't peek at it. So in statistical inference, you have an idea of the distribution that you're working with and the qualities of the distribution, or how you're determining how uncertain you are, and that's how you're determining the quality of your model. In machine learning, the way that we do this is with cross-validation. So the data that we've set aside that we don't look at, our performance on that data is how we determine the quality of our model in the end, is how well it works on data that it wasn't trained on. And then this is probably going to be the most time-consuming part of most machine learning workflows, at least in my experience. You want to figure out what features are actually useful for your problem. And you might want to even develop some new ones, and that's called feature engineering. An example might be, I have information on a bunch of students, and I'm working in admissions, and I want to predict what students are going to do well at a college based on their high school information, or sort of their academic record in high school. So something that I know might be important is maybe the quality of their high school. So maybe they didn't have access to a lot of resources. Maybe they're from a part of the world or a part of the country where they don't have a lot of funding. They didn't have access to books or computers. And if they're still doing well in their high school, even with limited resources, maybe that's something that I can think is going to mean that they're going to do really well in higher education because they have a lot of sort of drive. So something that I could do for future engineering would be to include a measure that I develop using my expert knowledge of high school quality or the resources available for a given high school, and use that to inform my prediction about how well students are going to do in college. And then once you have your features figured out, you can actually get to training your model. So the first thing you want to do during training is specify what your model will look like. So the qualities that your model will have. You're going to want to pick your particular algorithm that you're using. So you might be using, logistic regression. You might be using random forests. So XGBoost that we're going to talk about is a type of random forest. You might be using deep learning. You might be using k-means for a clustering project. You might be using support vector machines. So I'm just trying to come up with some machine learning algorithms. And then once you've picked what your algorithm is, you're going to want to pick the hyperparameters for the particular project that you're working on and specify those. And then you train your model. So you give your model your labeled data, if it's supervised learning, or just your data if it's unsupervised learning. And then your model will do whatever sort of training it does based on the type of model it is. And then once it's done, you might choose to do several different models, training them either using different algorithms and comparing them, or using the same algorithm but different hyperparameters. So one common way to pick the hyperparameters for a specific project is called grid search. So you sort of define the boundaries of your hyperparameters, and you're like, I'm going to pick, every 5 values, and then for parameter 1, and then every 5 values for parameter 2. Actually using random search, so instead of sort of like stepping through by 5s, picking points randomly from within that space, turns out to be a little bit more efficient because you don't know the sort of the loss of that space. It could be like there's a little minima here, but you don't know about it because you've sort of picked around it, and if you have randomly picked it, you're more likely to be at a minima. So random search is generally more efficient. And then once you've trained your model, it's time to evaluate it. So the data that you set aside earlier, you'll take that and you'll apply your trained model on that data, and you'll get out your labels if you're doing supervised learning, and then you'll compare it to the actual truth, and you'll see how well you did. So that's sort of the general flow. And there are 3 things to watch out for: underfitting, overfitting, and leakage. So leakage is when the example I gave earlier with the elephant, and you're actually looking for acacia trees in the background, is when you happen to find a feature. There is a feature in your data set that's extremely helpful for what you're trying to predict, but it's not actually informative about what you're trying to predict in the rest of the data set. So in another example, you have an image data set and you're trying to decide whether it's a picture of flower A or flower B, and all of the pictures of flower A were taken with the same type of camera. So you might actually build a camera detector, but there's no reason why all of the pictures ever taken with this particular model of camera are going to be pictures of flower A. So you want to make sure that you are actually doing the task that you think that you're doing, and not actually a second task that happens to have the same success parameters. Overfitting is when your model, so the way that machine learning models in general work is that they reduce the error between the points that you're given and the place where the model is over time, and eventually it will get to the point where you're describing the distribution of the data that you've trained on, and at that point you are definitely overfit. And the problem with that is then when you have different data, like your cross-validation data, it's very unlikely to follow that exact same distribution. So you'll have a higher error on your testing data than your training data. So you'll see sort of over time as your model trains, you'll start to see a divergence between your training data and your testing data, and that's the point at which you know you've overfit. And then the final problem is underfitting. And this is more of a problem sort of during model training. It's where there's additional information in your data that you could be using, but you don't have, you haven't trained your model long enough, or you don't have enough features, and you're failing to have a model that's as accurate as it could be given your training data. And generally, the solution there is going to be training for more rounds. So whatever you're doing, generally there's sort of an iterative process, and if you stop too early, you're going to be underfit. And if you stop too late, you're going to be overfit. So finding that sweet spot in the middle is one of the challenges of machine learning. And there's a little, nope, get bigger. Nope. Interesting. All right, so this little picture that's a little bit small and I can't make bigger, and I'm sorry about that, shows the overfitting and underfitting. So if you have this sort of parabolic distribution of points, you want to describe them with more or less a parabola. And if you describe the precise placement of every single point, you're unlikely to get that same placement of points in future data samples. So this is going to have high error on future data samples. And this underfitting is just a flat line, and it doesn't, Ashkit says it's, perfectly clear. Thank you. And you can see that there is additional information in the data distribution that we aren't capturing here. So that's the general idea. One sec, I'll take my sweater off. I'm getting warm. So machine learning, you want to split your data, do some feature engineering. If you're working on a problem that's something that you've worked on before, you probably already have a good idea of what some useful features could be, or maybe you've read papers on a similar topic and you sort of know what other people tend to use. And then specifying what your model's going to look like, picking some hyperparameters, training your model, maybe doing some tuning is what it's called when you change your hyperparameters to improve the performance of your model, hopefully improve the performance of your model. And then finally, you apply your model to your held out data and you see how you did. So let's start looking at some code. We're going to be working with this XGBoost model. So XGBoost stands for Extreme Gradient Boosting. It's a type of random forest. So random forest is an ensemble model of trees. Trees are you might be familiar with classification and regression trees or CART. Let's actually quickly look at a tree model. Machine learning. I just want a picture. Nope. There we go. So the classic decision tree is going to have sort of a branching structure, and in each branch you look at the value of a specific feature, and then depending on that value of feature you continue walking down the path. So each data point would say, this is for the Titanic. Was the person's sex male? If no, there is a 36% chance that they survived, and 0.73% or 0.73 of the data fall under this particular branch, and so on. An ensemble is a model that is a collection of different models that are the output from one model is put into another model, or you look at multiple models simultaneously and then you average across them, which is the way that XGBoost works. And this allows you to have more flexibility in the final model. So, for example, if we were doing an ensemble model, we might have this model And then we might have a second model that says, is your sex male? And then in the no column, we have an additional branch, maybe like what was the class that you were in the ship. And then when we ensemble those together, we'll have more final fine-grained distinctions in our final model than we did in any of the input models. And in general, ensemble models are more powerful, tend to be less likely to underfit, can be more likely to overfit because of that additional power. And the sort of way that extreme gradient boosting, it's extreme with an X, like it's a 90s, I don't know, extreme sports thing, is that we start with a naive model, so just sort of a random tree that we generate based on our model. And then we look at the errors from that tree, and then we build a new model that predicts those errors. And then we add the model to the model that we already had, and I believe it's averaging in extreme gradient boosting specifically. And then we run our data through again, and oh look, we have different errors, and so we try to predict those errors. So we're sort of converging in on the specific qualities of our data set, and we want to stop it before we overfit, is the general idea with XGBoost. So let's actually, I believe there's a workbook for this. This is, nope. There we go. There's a workbook. So this is what was previously part of the R curriculum in Kaggle Learn, and we've actually removed a couple of lessons from Kaggle Learn, but if you search for machine learning with XGBoost in R, you should be able to find it on the platform. We haven't removed any of the notebooks, we just took out the links from Learn. So let's make our own copy. If you haven't been in kernels in a while, you may notice that it looks a little bit different. We recently launched for everybody our new editor. It's very fancy. Some things you may notice, by default, the sessions are started in Python. If you're an R person, you can set it to R in the settings tab over here. We have GPU access, internet access, that's the same. You can also install packages, and if this doesn't work, and sometimes it doesn't, I've written a little kernel to help you install our packages that you can check out if you're looking for something specific, using dev tools. Sorry, this is the first live coding stream where my test account has had the new editor, so I want to show it off a little bit. And if you want to get rid of this panel, zoop, goodbye. Some things that I'm particularly excited about: we added a way to run all of the cells before and after your current selection, which is something that people have asked for. You can also stop execution once you've started a cell if it ends up being pretty slow. And you can always do these with the little buttons by the side, but they're in the little drop down as well. And you can also move cells in your notebook, which is something that a lot of people had requested and is making my life a lot better. So I have actually picked a example for us to work with. So we're trying to predict whether a horse has colic will survive or not. So colic's like a digestive disease, I guess. I don't know. I think like horses like cough a lot. I used to know what colic was. So we're going to figure out whether or not they're going to survive or not. And then there's a second set where we will be using a different model and determining whether or not zoo animals do something. I forget what the zoo animals do. Whether or not it's a mammal based on sort of qualities that it has. So the first things we want to do is we want to read in our libraries. I like Tidyverse. It's a meta package that combines a lot of packages that have a lot of nice utility functions. If you're more of an R person who is familiar with data.table, of course you are welcome to use that, and I just like Tidyverse. And then we want to use the XGBoost library. So XGBoost is actually implemented in C, and this is an R language wrapper for it. So you can use XGBoost in R, Python, I think maybe Java, but it's not, but we're going to use R today. R says, oh, that's how you move the cells. I thought it was going to be some drag drop thing. I want that. I want that very much. Apparently it's hard and involves a lot of front-end engineering or something. But yes, it's been requested. But for now, you can use the buttons. Okay, so some other things that I'm doing in here, I'm reading in the CSV file. So in Kaggle, you can see that I have two data sets that I've read in already, this new animal classification and this horse colic data set. And in the horse colic data set, I have this file horses.csv, and the address of that is up here at the top. And we've also added some, I'm really zoomed in, so this is not usually this small. We've added some nice quick ways for you to check out the data set a little bit more quickly without having to read it in and actually make all of these graphs. So that's another nice thing. And I am setting a random seed. So I'm going to do some things that are random. And because I've set a seed, the next time I run this code, I'll get the same output out. And if I don't do this, every time I run the code that has a random component, I'll get a different output out. So if you were following along, you'd see something different. And this is for reproducibility. And then here I'm actually shuffling. So I am assigning to the colic data set, and I am sampling the rows, 1 through the number of rows. So this is just sort of a random shuffle of the data that we already had. And then I'm adding a column for the outcome that I want to predict, whether or not it's lived. And I just hit Control Enter to run this cell. So you can see I'm attaching the package, etc., and I don't actually need that to be big, so I'm going to collapse it. And now I have some things that I need to do. So one thing I want to do is remove information about the target variable from the training data. So if I have a column that perfectly predicts whether or not a horse with colic is going to survive, I want to remove that, because otherwise I'll have leakage and I'll be using that column, which has information that I'm not going to have at the time that I'm actually running the analysis when I care about it. So what was this called? I did write this lesson, but it was a long time ago. It was almost 2 years ago at this point. So I want to remove the column outcomes. So colic, actually, first of all, just let's quickly look at the head of this so we can get an idea of what it looks like. This is what it looks like there we go. In outcome, so this is the column that has information. I have added a column lived that has a Boolean because that's going to be easier for us to make a matrix from when it comes time for that. So we want to remove the column out from, so colic, and then we're going to use a pipe and select. I'm going to select everything except the row outcome. All right. And then we're going to convert age to a numeric variable using one-hot encoding. So one-hot encoding takes a categorical variable and changes it into a number of columns equal to the number of categories in the categorical variable. So categorical variable would be something like horse breed. So is it a quarter horse, or an American curly hair, or a pinto, or I'm out of horse breeds. Is it one of those things? So you'd have a different column for quarter horse, curly hair, Pinto. And then for each horse, you'd have a 0 if it did not belong to that category and a 1 if it did. So reading across each horse would have a 1 in one of those columns, correlating to whatever breed it is, and a 0 in the other column. So that's what one hot encoding is. I don't know why it's called one hot. And I'm actually going to go back and look at the lesson so that I can see how I did that and copy and paste. There's nothing wrong with copying and pasting. Let's see, one hot. Hot. All right, so we are going to use model.matrix by country -1 of the specific column that we're interested in. All right. And then excuse me, pardon me. Sorry, I can't mute because that unseeks the audio and the video. Copy. All right, so we are selecting. So let's call this age, and then the specific column that we're interested in is age. So let's do that. Object age not found. Oh, right. It's in colic, the data frame colic. We want the column age, and also there should be a space there. Country not found. Oh, okay. Okay, I'm picking up what you're putting down. I actually need to give it the data frame, I think. Ken says, the one hot encoding sounds kind of like a pivot operation. I'm going to be honest. I don't know what pivot tables are. I know they're a thing. Does someone who knows what pivot tables is tell Ken, please? Object age not found. All right. Categorical disease info. Okay. Disease info. Country is definitely the the column. Disease info is definitely the Why does it not work? The joys of live coding. All right, so let's really quickly check the structure of colic. Oh, age isn't capitalized. Soup. All right, and now when we look at age, we should get a new data frame. So the possible ages are adult and young, and we can see all of these horses are adult horses, and then these two here are young horses. Okay. Oh, Ryan says it comes from digital circuits. You send output out of one of the pins. That pin is considered hot. That's why it's called one hot encoding. Ryan, you wouldn't lie to us, would you? You wouldn't tell us lies. I trust you. But also, this definitely sounds like something that might be a lie. I'm skeptical. I will look it up. Source, Wikipedia. Okay, well, it is possible that someone would lie to Wikipedia, but if there's one thing I know about Wikipedia editors, it's that they are pedantic and on their grind, so I'm inclined to believe Wikipedia. Okay, and let's actually add this to our existing data frame. So colic, and we're actually gonna, we're gonna C-bind. We're gonna C-bind, I'm sorry guys. lossy binding can take a while because it requires re-indexing, so you don't always want to do it. Actually, let's put age at the end. All right. And then we want to select only numeric columns and remove rows with NA values. So what we're going to do before we feed this into XGBoost is we're going to convert it to a XGBoost specific data structure that is called, I think, a D matrix, and it's a specifically like compressed matrix, because the matrix we're going to give it to begin with is very sparse, and it has to only have numeric variables because you can only have numbers in a matrix, and it will make it much faster to train. So I'm trying to remember how I did this previously. Did I just use isNumeric for each of the columns and then do it that way? Whether species is domestic, list of all the species, convert to a matrix using one-hot encoding, add it, convert to a matrix. I'm pretty sure there's a way to do this with select. Let's see. So select is a function. I'm going to gonna Google this. Tidyverse select is numeric. Yeah. No, there's definitely a tidyverse way to do this. Go away. Select if. There we go. So it's select if and is dot numeric, and then let's just quickly check the head of that to make sure that it does what it say it do. It do say what it say it do. Okay, excellent. And we also want to remove NA values. And it looks like some of these columns have a lot of NAs in them. So what I'm going to do is I'm going to remove columns that have a lot of NAs in them. And then I'm going to remove rows that have a lot of NAs in them. Because if I just remove every row that has an NA and some of the columns have a lot of NAs, then we might end up removing a lot of data that we don't need to, if that makes sense. So what's a good way to quickly see if there are a bunch of NAs in a data frame? I know there's a really fast way to... I think missing no is a... I'm pretty sure missing no is a... yeah, that's a Python package, because Alexi is definitely a Python programmer. Are summarize NAs. Testing, removing rows, NA omit. No, I just want to quickly, I want a way to see if it's missing visually. Okay, is there a way to count the number of NAs per column? I'm sure there is, sorry. I'm just trying to figure out what it is. And it's pretty much anything matrix-based, it's a good idea to check for NAs before you start. For example, I know that in the R version, the R Keras implementation, if you have any NAs in a matrix that you feed into, certainly any of the RNN family of things, you will get a completely dead network, like all the cell weights will be 0. It'll just train everything to be 0. Ryan says in Python I would do isNA.sum. what do we call it? We call it colic. I'm pretty sure this will give us the sum over, okay. I think we need to do apply, but I think we need to do apply colic over 2 is NA. Yeah. And then, I think from there you need to do call sums. Oh, Alfonso says skimmer. Yeah. And Apprenda says summary. Let's do summary really quick. I didn't remember if that was in summary or not. Okay, yeah, it does have NAs. So we have a lot of NAs in nasogastric reflux. pH has a lot of NAs, as does abdomoprotein. So I'll probably get rid of those 2 columns. But I also really want to quickly see if skimmer will work. So skimmer is a really nice colic. So skimmer is a really nice visual representation of summary, and it looks like it doesn't show you. Oh, okay. It does. So it'll also give you like a little So the really nice thing about skimmer is it shows you a little histogram, and it looks like the histograms aren't showing except for NAs. So this skimmer in particular seems like something that would have problems with the HTML rendering bug in Jupyter that is a known bug and is never going to get fixed in base Jupyter. So let's remove nasogastric reflux. pH is the one that we want to remove. And then we also want to remove abdomoprotein. I'm guessing these are the results of tests, and if the test isn't passed, then if the test isn't required, then you're not going to get a result for it. And then I'm going to, so I've removed, so I have removed those 2 columns, and then what I'm going to do is I'm going to filter so I want to filter rows that contain an NA, and I think there should be a little code down here if I remember correctly. No, this didn't have any NAs in it. I'm gonna Google for this one too. Remove all rows with NA. I guess I can just do NA omit after that. Complete cases. All right. So I'm just reading this and not reading it aloud, which is, great TV, good content, Rachel. Okay, from here we want to na.omit. And if we did na.omit first, we'd end up removing a lot of rows that we didn't need to remove. All right, so we shouldn't see any NAs here, and it looks like we don't. And from here, we want to remove anything that's not numeric. Right. And that was, I believe, select if, and then is dot numeric. Okay, actually, let's do that first, and then do these. Move this all together. And then I'm really quickly going to check the head of that output before we save it. And that looks good. Those are all numbers, and they are all, looks like, not NAs. Okay, so let's get rid of these cells we didn't need. Our trash can is back. We briefly removed the trash can icon here, and it is now back, much to my delight. I like the little trash can. And then we'll save this as colic. I know that I'm writing over my own data frame, which isn't necessarily a great idea, but I'm doing it anyway. All right, and then we are going to split it into training and testing data sets. And I believe the very dumb way that I did this, it's not super dumb, it's kind of hacky. It's a little bit hacky, is to, decide the number of training samples based on getting the length of the labels that I'm interested in. Copy this, and then we will paste it and modify it, which I realize is a large part of this live coding session, but that's how it do. So, and we were interested in an 80-20 split, which is what that is, except instead of the length of zoo animals, oh, let's get rid of this as well. Goodbye. We want to do the length of colic.lived, which is our target variable. Ryan says, ignorant question time. How were we supposed to delete cells without the trash can? Just know the keyboard shortcut? It was under the edit menu, and it's still there. It's just, I don't know. It's like, it's so much moving of the mouse, man. So many clicks. Ugh. I don't have time for that. I'm a busy data scientist. And then train data, train labels. Oh, that's right. We need to separate out the data and the labels. So let's actually let's do that before that, even though here No, I was going to move the cell up. We actually do need to do this secondly. So let's just move these around a little bit. So the value of vectors that we're interested in is here, and let's call this labels. So I'm taking the lived value out of the colic column, out of the colic data set, and I am calling that labels. And then I'm getting the number of training samples, which is just 80% of the labels. And then for my training data, I'm taking colic 1 through, so that's the number of rows, and then we want everything except lived. Is that gonna work? I don't know if that's gonna work. Let's really quickly see if this works. I don't know if you can do negative index of columns. Yeah, you cannot. Blah, 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 blah. Actually, let's do this labels, and let's do this features, and that's gonna be colic, and we're gonna select. So we're just gonna have a version of it that does not have lived in it, and then features, and then labels. All right, so here is our training data, and then our testing data is going to be the test data. We're going to look in the features data frame, and we are going to get from, so this right here is from the first one to the 80th percent one. So we want the number of training samples to the length of labels. And then we want, oop, that's not gonna work. And then we want all of the rows, and then the test labels. We want the labels vector that we've extracted, and then we want the same number of testing labels. All right, I've made an error. Lived, not found. Huh. Did I forget to remove it somewhere? Is character X lived, not found? Colic select lived. Is it not lived? That is what it's called, yeah? Did I remove it at some point that I don't remember? Yeah, I for sure did. Is it because it is a Boolean? Yeah, I think that's what I did. I think when I removed it, when I removed everything that wasn't numeric, I also removed my content, my target variable. So that's a problem. Good job, Rachel. Let's call this colic cleaned. Oop. Nope, you go away. So, do we have lived here? We do. It's logical. Okay, so if I want things that are numeric and logical, or is dot operations are only possible for logical, numeric, or complex types. I'm going to do this in the dumbest possible way. I hope you guys are excited for this. I'm going to cast it by hand to be numeric. Professional data scientist Rachael Tapman. And then we want the cleaned version, and then we want the cleaned version. And does it work? It does not, because I have misspelled labels somewhere. I think it was here. Yay! Excellent. And then the final thing to do is to convert them into data matrix. And I know that this has taken kind of a long time. Make sure our target variable is numeric. But as I think I mentioned, at least in my experience, this sort of like cleaning and preparation step does tend to take the longest time. Esdras says, I think if you do 1 through number of training samples. Oh, for where I had the labels problem. Yeah, I think it should work now, but thank you. And finally, we want to convert them into D matrices, and I don't remember what the syntax is for that. Aha. Copy. So what it wants is, and let's call this, instead of zoo, let's call it colic, because this is our colic data set. Colic. Our data is our train data, test labels, test data, test labels. So the way that the D matrix wants data to be handed to it is with the data and then the label as a, I believe it will take a data frame as long as it's all numeric. It will not. Let's convert this to a matrix and see if that works. Yeah, that should work. Esdras says, You're going to have the same number of training samples in training and test. I mean the same row corresponding to number of training samples. Oh, I see. We're double dipping. Yeah. I see what you mean. +1. So we were including the last row of our training table and of our testing data in our training data is what Esdras is saying. And that is not so good because it means that we're going to have probably artificially inflated performance in our testing data. Okay. And we haven't actually done any machine learning. We've done all the preparation work. So what we will do next time, and it might be at a slightly different time. I'm going to be at Next and Kaggle Days all week next week, and I'm going to be flying back on Friday, so I will stream when I get home, and who knows when that is, because flights are a little bit unpredictable. We will actually train our model, and then we'll do some tuning, and we'll do some examining, and we might actually do the zoo model as well as the colic model as we've done. Let me commit this. So if you want to work through this workbook yourself, you can search for machine learning with XGBoost in our workbook and work through it yourself. Check your understanding. Ashka's going to be at Google Cloud Next. Excellent. I'll see you there. Hopefully I'll see a lot of you. And I will try to do the reading club next Wednesday. We're still working on that, context encoding the Elmo paper, if you're familiar with it. But I think we might finish it up this week. And then I will be back next Friday, maybe not exactly at 4:00, but I'll tweet about it and let you guys know when I'll be streaming. So hopefully this was helpful for you guys, especially those of you who are a little bit newer to data science. And I wanted to sort of give you a sort of overview of machine learning and how it's different, and then spend some time working through a problem and sort of showing you my process, which does involve a lot of Googling for things because that's the way it works. And I will talk to you guys next week if you come back next week, and I hope to see you here if I don't see you in person first. So have a really good weekend and enjoy the sunshine if you have sunshine where you are. Bye.